content screen. What happened? Whiteboard. Yeah, here it is. Oh, still not gone away. Yeah. So anyway, this let's clear the screen. Any questions from the previous class? So as you know, we were talking about plasmid stability. Can all of you hear me clearly?
Yes, sir.
Yeah. So as you can see that we were talking about plasmid instability, essentially the problem of plasmid free cell emerging uh, uh, in the culture. And as I said, as I pointed out, that this instability has essentially two components. The process of emergence from this is 100% cells, 100% recombinant cells, and they don't emerge for a long time. It's actually not 100%. It may be 99.9%, 99.99%, and so on and so forth. Here it is 99.99%. Here it is 99.99%. And here it is 99.9% and so on and so forth. So it's actually the plasmid free cell is emerging very fast, but you can't see it at all. And suddenly, at some point of time, the plasmid free cells sort of tend to overtake very quickly. From 99 becomes 99, then 90, and then 9, and then 0.9. So clearly you can see that this whole process, this is a real problem. Just hold on. Hello? Are we in two? Could you hear what I was teaching, or was it just all? Hello?
So we
Sir,
cannot
you
hear.
weren't audible.
Sir,
When?
yes, sir.
Could you see the whiteboard?
No, sir. No, sir.
So you have been, all the time I've been talking, you could not hear a single word.
No, sir. No, sir. Till now, we didn't hear anything.
Oh, well, that's very amazing. You people should then send some kind of message. I mean, I've been teaching when I sort of stop, and this is the whole problem with Microsoft. So whatever I recorded, you did not see at all? Recording was also not good?
No, sir.
This is amazing problem. I've taught for 15 minutes, 20 minutes, and all that is gone. This is a crazy business. Hate this. Can you see this board?
Yes, sir.
Yes,
Now we can
sir.
see.
That is why I keep saying you people should keep talking. You people switch off your mics and don't say anything. Then how will I ever understand what has been taught? Did you hear all these things that I taught for the past 15-20 minutes?
No, sir. Nothing.
Well, amazing. I mean, you people have to interact. I mean, right now you're on, right? When you went off, nobody said anything. So please, for heaven's sake, talk. Don't fall asleep in the class. I can't see you because I have to put the whiteboard on. So whatever has been taught has now assumed to be taught. So how much of the class did you hear? Did you hear about the previous part of the class where I talked about time course and all that? No. You have not heard a single. You have not heard of a single minute of the class? Okay, wow, that's amazing. I've taught for half an hour and nothing has registered, and you guys are sitting quietly without even. Please note down my number 99106 if you get 45903. And if you get cut off from the class, please call and say we are not able to hear.
Sir, can you please again say your number?
It is written on the board. Can't you see the whiteboard?
I can see. I can.
Okay, this is very tragic and irritating. I don't know how to do this. I don't know. Well, okay, let's begin the class once again. If this is the way it goes on, then we are going to be in very major trouble soon. I was talking about plasmid instability. Now, every 5 minutes, I want a response. I will keep this thing on. Otherwise, you people, I mean, there's no other way to do it because none of you ever respond. I mean, I'm being harsh about it. I'm upset about it because you cannot teach half an hour class and then be told that we have not heard a single word and repeat the whole class all over again. It's lost. The whole flavor of teaching is lost. We were talking about the fact of plasmid instability, and two things determine plasmid instability: emergence and overtaking. Okay. Oh, well, I told you very interesting stuff, but I mean, this is an amazing situation. Anyway, so the probability of emergence of plasmid free cells is determined by 2 raised to the 1 minus n, where n is the copy number or actually the discrete number of copies of the plasmid. Okay? Yes?
Yes, sir.
Okay. Now, this n can be very small for small copy number plasmids, and if they undergo random partitioning, then this probability will be pretty high. If this probability is pretty high, then you will have random partitioning, P will be very large. So what happens is that for small copy number plasmids, they do not undergo random partitioning, the binomial function that we are talking about here. They undergo partitioning in ways which are determined by, which is called strict partitioning, determined by something called the partition locus. This partition locus ensures there is it's a part of the DNA which is there in the plasmid, and when the plasmids tend to divide into two plasmid daughter cells, they are joined at this point by the partition locus, and this joining point is also joins at the midpoint of the septum formation of the daughter cells. So one plasmid goes this side and one plasmid goes this side, thereby ensuring that the probability of plasmid free cell emergence becomes effectively zero. Because now the partitioning, when this cell is dividing into two daughter cells, 1 and 2 here, then one plasmid is on this side and one plasmid on this side of the wall which separates the two daughter cells at the point of separation. This ensures that plasmids, especially small copy number plasmids, are inherited exactly equally and not randomly, just like high copy number plasmids. This partition locus has been cloned and introduced into large copy number plasmids, and that also tends to make the partitioning not completely random but not completely perfect, and reduces the probability of plasmid free cell emergence. Is this clear? Are you hearing me? Hello?
Yes, sir.
Yeah, because you know, it's a really upsetting situation. So the plasmid free cell emergence can be slowed down by the process of trying to reduce P to values less than given by 2 raised to the 1 minus n, because this number might be very small. It might be 10 raised to the minus 5, but if you can make it 10 raised to the minus 7 instead of 10 raised to the minus 5, you could still achieve something very useful. For example, now let us sort of, this is all, everything has to be repeated. It's quite a. For example, please remember that when we were talking about this is the number of generations of cells, and this is the percentage recombinants. Can you see the graph?
Yes, sir.
And I gave you a plot like this. Now remember that this is 99.99%. It is not actually 100%. Or 99. And this is 99.99% or something like that. And this is maybe 99.999%. So, as far as we are concerned, the emergence of plasmid free cells is a kinetic phenomenon. It's a kinetic phenomenon which depends on the number of generations that have elapsed. So, if the number of generations which elapse in a fermentation at the end of fermentation is till this point, then as far as we are concerned, even though this is an unstable system, our fermentation ends here. And therefore, we have complete perfect stability. But if my instability were to be like this, then I have so much of instability at the end of the fermentation run. Suppose this is 10 raised to the minus 5, P is equal to 10 raised to the minus 5, and this is P is equal to 10 raised to the minus 7. So the idea of any design of reducing the probability of plasmid free cell emergence is not to make it zero. I don't want 100% stability. It is to make it such that at the end of the fermentation, plasmid free cells are not present. Remember that, do a little bit of arithmetic. I have 1 ml of culture, and it becomes 1000 liters of fermentation run at the end of it. How many? 1000 liters. How many generations have elapsed? What is the number of generations that have elapsed from a 1 ml culture, let us say with a cell count of 10 raised to 8 per ml, to let us say 1000 liter culture with a cell count of let us say 10 raised to 9 cells per ml. Maybe it's more dense culture. What is the number of generations that have elapsed? Can you hear me? Hello?
Yes, sir, we can hear.
Yeah, so all this has been taught. As a fact of it, I thought I had taught all this in the past half an hour. So now can you tell me what is n? The number of generations that have elapsed. Remember, one cell becomes 2, that is 1 generation. 2 becomes 4, that is another second generation. And so I want to know what is the number of generations for a 1 ml culture with a cell count of 10 raised to 8 cells per ml, becoming a 1000 liter reactor with 10 raised to 9 cells per ml. So what is N1 here? What is the total count of cells here? Can you tell me? Well, come on. That is why
10 to the power 8.
10 raised to the power 8.
I mean, if people don't talk, then we don't know whether you've disappeared or I have disappeared. please wake up. What is N2?
10 raised to power 12.
9 into 10 raised to the 3. And please remember, ml and liter are also,
Yes.
there is a 10,000
Again,
factor.
10 to what? Yes.
So how much is that? 10 raised to
15.
15. So come on, tell me, what is n? These are simple childish, I mean not childish, 2 raised to of n, where n is the number of generations, is equal to 10 raised to of 15 upon 10 raised to of 8 plus 10 raised to of 7, right? So take log n log 2 is equal to 7. And so n is equal to 7 divided by about 0.3, right? Yes, yes. Let's say 21 or 22, whatever. So 21 generations will take you from 10 raised to of 8 cells per ml to 10 raised to of 9 cells per ml of a 1000 liter reactor. If this was 10,000 liter reactor, then it would become 15, 16, this will become 8, this will become 24, 25 generations. So notice that usually fermentations end in 25 generations. If you start with 1 ml culture and end up with, say, a 1000 liter or 10,000 liter reactor, you would end up with about 25 generations. So the idea is to keep it stable for 25 or 30 generations, not more. 25 to 30 generations of stability is enough to guarantee that your life is easy. Okay, so you're not looking for 100% stability. You are trying to look for reducing emergence and reducing the overtaking of problem. So this is the story that I was telling you guys about, I mean, and which of course all got missed, is that when I went to with my colleagues in Cambridge, they were asking the opposite question. How is it that in evolution, in nature, plasmids retain their survival forever? That's not for 25 generations. They have been there for millions of generations. So I said, well, that's a very interesting question. He was asking the opposite question as a biologist. So it turns out that the same argument is there. So he was asking the opposite question. How do plasmids retain their ability to survive forever? So it is no longer the case that I'm trying to make it for 25 generations. Stability. These are stable forever and ever. And it turns out that they have the same problem. Normal plasmids have the same problem. The probability of plasmid free cell emergence is given by 2 raised to 1 minus n. And n, as I pointed out, is the discrete units, not the copy number. It is the discrete units of plasmids that are there. And if plasmids form multimers, then it will be inherited by one daughter and n will be counted as 1. But if it is a monomer, so a multimer would be inherited as 1, but if it monomerizes, then it would be 4 units, so the probability will be lower. So to increase its probability of inheritance, hence reduce this probability of plasmid free cell emergence, you need to convert the multimer into monomer. Can you hear me?
Yes, sir.
So it turns out that this is a very slow process. Now, making monomers to multimers, plasmids tend to multimerize very fast, but multimers to monomers is a very slow process. So the plasmid has to ensure that multimers form monomers and only then the cell divides. Can you hear me?
Yes, sir.
Yeah, it's saying that internet is
Yes,
poor
sir.
quality. Yeah, so now the problem is that multimers becoming monomers is a problem. And if it does not monomerize, the probability of plasmid free cell emergence becomes large. So, and this is a slow process. So what does the plasmid do? What mechanism has the plasmid evolved to ensure that this, and the most amazing answer to this question is that the plasmid has evolved a checkpoint to cell division. So when the plasmid is present as a multimer, when it is present as a multimer and it has not yet monomerized, it actually generates a small RNA molecule. It actually produces a small RNA molecule which we call RCD, regulator of cell division. And this RCD molecule, when it is produced, prevents the cell from division, prevents cell division. So imagine, we tend to think of plasmids as something which are inert and present inside the cell and somehow they are managing to survive. But you know that question that you were asking, that well, billions of years they have survived inside cells. They would have learned to interact with the cell and to ensure their continuance inside cells when the cell divides. And how is that ensured? That by developing very clever mechanisms which prevents the cell division to take place by generating. So only when it becomes a monomer does it allow the cell to divide, because it now knows that because there are multiple copies, one or the other, all the daughter cells will get the plasmid, and thereby they will ensure their continuance. So you have had very interesting evolution happening between plasmids and cells. So it's not a simple. So these are very fundamental and interesting biology questions that sometimes asking gives you very novel and very surprising results. And of course, life then become very easy for us. Why? Because we took the normal cell, normal E. coli cell, and normally we were having this plasmid inside it with the gene of interest. What we did was we put another plasmid inside and we put the RCD inside. We put the RCD inside, this RCD inside it. And when we overexpress this, what would happen? The cell division stopped. The cell division stopped. And so we got cells which were not dividing. So my colleague, who was an Englishman, had a very nice description for it. He called it the quiescent cell. Quiescent means resting, active, but resting. So the cell was active metabolically, but not dividing, but non-growing. Not growing, non-growing or resting, which means non-growing resting cells, which means the cell is not dividing because of the RCD is preventing the cell from dividing, but no other damage is being caused to the cell. You are not stopping the growth by some clever mechanism. You have used evolutionary strategies of the plasmid to prevent cell division.
Yes, and sir, what is there in that? What is specific about that special a small RNA molecule so that it prevents cell division? Like, if it is a small RNA molecule, how can it prevent cell division?
That I will not explain. That is something for you to read. I will not get into E. coli molecular biology because that will take you very far afield. I don't want to tell you about the altars and there are how the septum forms. I will ask you a very simple question as a change. Only when I ask questions, you ask questions. How does the septum form in the middle of the E. coli cell? Why does it not form here? How does the cell know what is the middle where the septum has to form? Let me ask a very simple question. You know everything about E. coli, right? How does the cell know that it has to divide in the middle? Not an easy question. Sometimes very simple questions can totally throw you. You always tend to think in terms of intelligence. But tell me what mechanism could emerge that the cell could locate its middle where it has to form the septum and divide into two daughter cells? Well, this has to be all the time we hear stories that one cell divides into two daughter cells. Yeasts do not divide equally. There is no binary division. Yeasts have budding. So how do you know that the E. coli cell divides into two exactly equal daughter cells and not unequal? And if it divides into equal, how does it know where to draw the septum in the middle of the cell? How does it locate its own middle? See, sometimes asking fundamental questions is a very interesting way to go about research. So how does RCD work? We'll tell you how the septum forms and how the septum divides. It is not a very easy mechanism. It's a very complicated mechanism. And I'm not going to talk about it because I'll go far afield from the system of enzyme technology. I am trying to tell you small interesting stories which are worth exploring for those who are interested. Really, the point that I'm trying to do is that we were looking at enzyme production, and what we did was we discovered that somehow it stops cell division. I do not care how it stops cell division. I'm an engineer. I know that this small RNA molecule, RCD, actually stops cell division. I clone it and express it. My cell division stops. What does it do? It does something amazing. It actually sees that it becomes quiescent cells, and once it has become a quiescent cell, my cell, all the metabolic energy inside the cell is no longer being used for growth. So normally if you take cells, look at cells, and you look at biomass in time, they grow like this. And the product also forms like this. Because product formation and growth are associated with each other. Or both of these utilize the process of DNA becoming RNA becoming protein. I mean, this is common to both growth and to protein production, because proteins are part of the growth process, cellular proteins. But now suddenly what you have done is that you have stopped the growth here. You have made it quiescent cell by overexpressing RCD. So all the metabolic energy for proteins comes into this. So my rate of production becomes much higher. So we could design a Q cell platform which produced proteins and did not produce the cell. So all metabolic energy was diverted towards product formation, making it a much better system. So sometimes you can make technology by looking at very fundamental discoveries. That is all that is the story, the moral of the story here. Okay, are you hearing me or has it disappeared?
We can hear.
Okay, thank you. Okay, so now let us go back. Let us not waste time here. Not waste time, and these are interesting insights that we want to tell you, but I don't want to spend time on this. So as I said, that as far as I'm concerned, I am interested in reducing emergence and overtaking. Now, how do I reduce overtaking? Now, I mean, I gave you two examples of plasmid free cell see, because once the plasmid free cells emerge, they are still in very, very small number. P is very small. P is of the order of tensor of -5 or tensor of -6. So the probability of plasmid free cell emergence is 1 in a million or 1 in a billion. It is the overtaking which actually ensures that this graph becomes like this. For a long time, it doesn't emerge. So notice that it's something like an inverse exponential function, starting with a very low value. Right? I mean, exponential functions look like this. But if you make this number very, very small, it will look like this, right? So for a very long time, it is this function here. So very low values is starting, and then slowly it emerges and becomes very large. So it is the alpha which determines this fall. If alpha values were low, this graph would go like this, or it would even be like this. In which case, for all practical purposes, if my fermentation ends here, I would still be fine. If this is where my fermentation ends, and so my percentage recombinants still remain high because this is number of generations that I want for a stimulator. Now, the most obvious answer to the prevention of overtaking is the answer that is there in the cloning process itself, which is that we are now cloning the plasmid, and the plasmid, when it is cloned, it also contains an antibiotic marker, ampicillin, for example. And so in the media, you could add antibiotic or ampicillin. Add ampicillin in the medium, then all cells which lose the plasmid, if the plasmid is lost in any daughter cell, it will not contain the ampicillin marker as such. And if it is not there, the cell will die. So if the plasmid is lost, the cell will become, so the plasmid free cell is also ampicillin sensitive, and the plasmid containing cells, the plus cells are ampicillin resistant, and so they should die. Now, it seems to be a very obvious and simple solution to such a complicated problem. It unfortunately does not work very well. There are reasons why it does not work. One is that all cells, when they have this ampicillin resistant gene, this ampicillin resistance arises out of the production of a protein called beta lactamase. Can you hear me, all of you?
Yes, sir.
Hello. So beta lactamase is the protein made by this ampicillin resistant gene, and beta lactamase degrades the beta lactam ring of penicillin antibiotics. There is a beta lactam ring for all penicillin based antibiotics, and ampicillin is only a semi-synthetic derivative of penicillin. I hope you know that penicillin, you've heard of penicillin?
Yes, sir.
And then penicillin, the side chain is removed and you make something called 6-APA, 6-aminopenicillinic acid. And from here, by semi-synthetic additions, you can make Novamox and ampicillin, and these are all the generic names of all the dogs and all the things that you buy in the market. So this is how you do it, right? Okay, you've not heard of this? Okay, let's forget it, but you should know all these things. So penicillin is first converted to 6-APA by removing the side chain, and different side chains are added, and that is why these are called semi-synthetic antibiotics. That is why these are called semi-synthetic antibiotics. And this, the fundamental principle is the beta lactam ring. And the beta lactam ring is destroyed by the beta lactamase and thereby degrades the antibiotic. Now, the problem with beta lactamase is that in the culture, when you grow it, so when you grow it in the culture, in the fermenter, then in the fermenter, the cell which is growing here is actually producing beta lactamase, and this beta lactamase here, is actually slowly leaches into the medium, leaches out into the medium. And this leaching of the beta lactamase then tends to destroy the antibiotic that is present in the medium. So that in the medium you have added the antibiotic ampicillin. Now this ampicillin in the medium, as beta lactamase leaches out, this ampicillin is destroyed. Can you hear me?
Yes, sir.
Yes. So when ampicillin is destroyed, then plasmid free cells which do not have the resistance can now emerge. Plasmid free cells can now emerge. So you think you have added antibiotic, but the antibiotic that you have added for preserving the plasmid containing cells, for preserving the same plasmid containing cells, have actually destroyed this antibiotic by the beta lactamase secretion. And so now these plasmid containing cells have ensured that plasmid free cells can now emerge. This happens especially with high cell density fermentations because each plasmid containing cell is leaching beta lactamase, and each of these beta lactamase leaching is actually going to prevent the plasmids from, which is going to allow the plasmid free cells to emerge because beta lactamase has destroyed the antibiotic that you have added. So it is not always a guarantee that when you add antibiotic in the medium that plasmid free cells will not emerge. So let us stop here. I mean, unfortunately, I'm pretty unhappy today because half the class, after teaching half the class, I learned that you people are sitting quietly and not saying anything. Let us not have a repeat performance of this ever. We don't have enough classes, and it is very tiring to repeat exactly what you have said half an hour ago. It destroys the whole pattern and teaching pattern of the class. So please, without my having to ask, are you able to hear? You people should say something from time to time. It cannot be a class which is completely, you are not quiescent cells, you're not resting, metabolically active, but completely resting phase. Please have some.
Before it cut like you said that I am going for something, that's why I didn't talk about.
Where will I go? When did I say I'm
No,
going?
sir. You said that just a second or just a minute. I am connecting something. You were saying.
I said I am connecting the whiteboard.
Yes, sir. After that, it didn't happen. Like.
Wow. Anyway, my mistake. Let us say. Let us assume it's my mistake. But let this not happen again. And one of the things that you should ensure is that that you should keep on talking in the class. And all of you, Ratnesh, not just you. I mean, it is good for you to talk, and I like it. But you should also give the opportunity to your colleagues to talk. Please remember that everybody has a fair chance. So I am not going to discourage you from talking, but I would also encourage others to talk, because one person taking over talking means that only that person is heard. And that's an unfair thing, and there's no way I can control a class where all of you are distributed in various places. So certain amount of decorum and mechanisms of running a class online has to be learned by all of us.
Sir, I had a question that.
Go ahead.
Sir, if we constantly adding ampicillin antibiotic into the reactor, does it work? Or
yes, it does work. Yes, it does work. Yeah, it does work. So you have to sort of estimate how much of the ampicillin has got degraded and add appropriately corrective action. And this has been tried out reasonably successfully. People, I mean, especially if you are producing enzymes which are drugs in the market, they get very, very angry. The drug buyers get very, very angry. A, because you have loaded the system with ampicillin, you are throwing out ampicillin in the medium, in the culture, and you are creating ampicillin resistant bacteria, because you cannot get it degraded very well, and you are carrying contamination of ampicillin from the media into your product, and all these lead to very serious repercussions, and Indians have been blocked from production of interesting enzymes for therapeutic use because of overuse of ampicillin.
okay, sir.
So these are very serious issues. So that is why I wanted to sort of flag it.
But sir, there is one thing or one more that if we are ensuring that there are also have the plasmid ampicillin, then those would more secrete beta lactose into the medium.
Beta lactamase.
Beta lactamase.
Beta lactamase is only secreted by plasmid containing cells.
So yeah, sir, so we are only growing plasmid containing cell because we are killing. So means I am saying that as the plasmid containing cells biomass increases, the beta lactamase secretion will also increase. So we have to overbalance during the adding of ampicillin into the medium. This factor means we take
the point. I mean, I think you have missed the fundamental point here. Plasmid containing cells produce beta lactamase. This leaches out into the medium, destroys the ampicillin. Plasmid free cell emergence is happening all the time because of poor or random partitioning, and small plasmid free cells are emerging. These cells, if they are not killed in the presence of ampicillin, can have a rate of growth which is much faster, and then they slowly start overtaking the culture. There is nothing to stop them from growing because the ampicillin has already been destroyed by the plasmid containing cells. So the plasmid containing cells are then completely overtaken by the plasmid free cells.
Okay, sir. Thank you, sir.
Oh, let's stop here. Thank you.
Thank you, sir.
Thank you.